Let's pause the music and see if the stream is on. The stream is on. The stream is. Yeah, it kinda is. The stream is. Yeah, it kinda is. Yeah, nice. Okay. Very nice. Okay, so today we're gonna learn about learning how computer vision actually works. Yeah, so in this tutorial we will learn how to train a convolutional neural network for image classification using transfer learning, and you can read about this more in this page. I can add that. It's fine. Quotes. So in practice, a very few people train an entire conventional or convolutional network from scratch with random initialization, because it's relatively rare to have a dataset of sufficient size. Instead, it is common to pre-train a conventional net on a very large dataset, like ImageNet, which contains 1.2 million images with 1,000 categories, and then use the conventional net either as an initialization or a fixed feature extractor for the task of interest. So these two major transfer learning scenarios look as follows. Fine-tuning the conventional net. Instead of random initialization, we initialize the network with a pre-trained network, like the one that is trained on ImageNet with 1,000 datasets. Rest of the training looks as usual. And the conventional net is a fixed feature extractor. Here we will freeze the weights for all the networks except for all of the final fully connected layer. This fully connected layer is replaced with a new one with random weights. Only this layer is trained. So what they actually do is import the Torch library. So we're gonna import it. So they import Torch, and then they also import the neural network from Torch. So from Torch.nn import the neural network, and then we also want to import the. By the way, this should be import, not from, and we gonna name this nn as nn, so we can relate to that import easier. Then we also import the optimizer, which is torch.optim, and we're gonna import it as optim. And then from this library, we want to import from this optimizing library. We also want to import the LR scheduler. And I think I typed it wrong. Yeah, there we go. Nice. And then we also want to import something from the backend, which is Torch.backends.could nn as could nn. And I think I also installed the CUDA successfully, actually. Which was just a small bit of a problem I had. So we're gonna import NumPy as NP as well, which will allow us to do more complicated computations with matrices and so forth. And since we want to use the Pytorch dataset, we also have to import Pytorch vision, because that's gonna allow us to access datasets that we haven't created by ourselves. And from Torch vision we also want to import datasets, which is how we're gonna get that. So datasets, and also modules, and also transforms, like that. And we also want to import matplotlib as .pyplot, actually, so we can module up the plots, and this is gonna be as PLT, so we can reference that. We need to import time, which will make us able to get the time, and also the operating system. And from this PIL, we want to import image, so we can reference images. And from the temp file, we import temporary directory, so we can create temporary directories. Now we want to see if we want to activate could n dot benchmark, which is gonna be true. And we also want to plt.i on this. And this should also print us an object, and I think I have to print it, but we can try it first. So let's test this. Yeah. So this failed to load image Python extension. You can ignore this warning, otherwise there might be something wrong with the environment. Okay, so if we instead print this, this should give us the same object, and we probably will get this warning all the time, but that's fine. So let's see if this is fine. Yeah, so we got the object, so that's fine. We can actually ignore this warning, that's fine, we don't need that. So this works, and we will remove this print. So that seems to be working. So now we're gonna load the data, and so we will use Torch Vision and Torch Utilities, torch.utilities.data packages for loading the data. The problem we're going to solve today is to train a module to classify ants and bees. We have about 120 training images each for ants and bees. There are 75 validation images for each class. Usually this is a very small dataset to generalize upon. If trained from scratch, since we are using transfer learning, we should be able to generalize reasonably well. This dataset is very small, but a very small subset of ImageNet. Download the data from here and extract it to the current directory. So we want to download the data, which we will do. And then we get a zip file, and I will have to extract that. So we're gonna open. You can either use your terminal or a file manager like this. I use Nemo, that's fine. And we're gonna extract it here. So we could extract it, yeah. So we're gonna extract it here, and then I will just see what type of data. Okay, so we should probably just move this whole thing into our directory that we have. And this will be in my home directory in the Pytorch tutorial, which is project files, and then also transfer learning, and here that should be here. So that's fine, and we don't need to save anything, so we can remove that. Now we should have the files here, so we have that. So now we're gonna define some data transfers. So the data augmentation or normalization for training, and just normalization for validation. And so this is going to be the data transform, which is the transform that's going to hold our data. And this is going to be a directory, basically. And the label here is going to be train, which is going to have a transform, transforms.compose. So it's a compose transform, which is going to include some adjustment, so to speak. So this is going to be transforms dot random resized crop, which is going to be 224. And we also want to have our transform random horizontal flip. And this will essentially just change the data so we can use it as we want it to. This wants to take an argument, and then we want to convert this transform to a tensor, which will make us able to use matrix multiplications and so on this. So we're gonna make it a Pytorch matrix, and then we will also want to normalize the values, so we have prediction values basically. And this will take in 485 and 0.456, and this will take in 0.406. So this is basically values that we give to normalizer, so we can essentially normalize the value dependent on these values. Just like that. And I will probably remove the music as well. I don't think I want that actually. So that's fine. And we also want to create a validation transform. So this is gonna have the label of val. and which is going to be a transform compose as well, which is gonna take in some arguments here. So this is gonna be a transform.resize here, and this will have 256, which is probably gonna be the size of the resize, and this will be transform dot center crop, right, which is 224, and transforms dot to tensor, so this will convert the transform to a Pytorch matrix, and this will also normalize the values as well. So normalize like that, and this will be 0.485, and it's the same values, I think. Yeah, it has to be the same values. So we're gonna copy this whole thing. Oops, copy this. Let's clip it like that, and that's fine. So this will be our data transfer, and then we have our data directory, which is directly to the data we downloaded, and this will be different from the normal path they have, because they have another folder called data, which is but I should just be able to type hyper optera underscore data. Optera underscore data, because of the position of this folder here. So I think that's fine. Now we want to link the image underscore dataset, or datasets because it's multiple, and we want to loop this. So we're gonna create a what do you call it? We're basically just creating a for loop here, and there's another way to create this for loop as well. And then now we're gonna get the path, and then join the data directory to get the data basically with an x value, which is essentially what the x value is gonna increase. So we're gonna join the data directory with a value of a value that is increasing by 1 every time the loop is running, so we get every data. And then we also want to get the data transform as well, so we're gonna get the data transform, which is gonna take index as well. And then inside of this we also want to do or x, right, in the train and val. Train, this should be a string, train and val, like that, and this should also be a string, like that, and I think that's fine. So now we're gonna do data loaders. So we can load the data. So data underscore loaders, right? No, loaders, like this, and then this is gonna be equal to also a for loop, which is gonna loop through the torch.utils data loader. Oops. Data loader, which is gonna take in. This is interesting. Did I type this wrong? If I do this, this is basically, yeah. So the data loader supports both map style and iterable style. Data loader combines a dataset and a sampler and provides an iterable oversize of given dataset. So this will give us the datasets that we want, but I wonder if I typed this wrong though. I might have. Whatever. Let's see if this works. So it's image underscore datasets, which is gonna take in the x value, which is the position, and then we're gonna add a batch size. The batch size is going to be equal to 4, and then we also want to have a shuffle to true. Shuffle is gonna equal to true, so the data is random, and we also want to have number of workers. So I guess this is able to work in parallel because we have number of workers, so we can utilize the data in parallel basically. And then we want to create a for loop as well, so we can iterate over it, and we are basically just typing 4x in the train, which is going to be a string as well, train and val, like that. Now we're gonna get the dataset size, sets underscore size, which is equal to another for loop, which is length of the image dataset we get. So this will be, in general, depending on how large the dataset is, and I guess it will be different for the different sets in the train and val labels. Like that, and then we want to get the class name. So class names, which is going to be equal to image datasets, which is train dot classes, right? So we get the classes like that. And now we're gonna get the device. And I hope this works. If this works, I'm gonna be super happy, because we know we're gonna use the CUDA version of Pytorch and not the CPU version. It's gonna be torch.device, and if we have a CUDA 0, if torch.CUDA is available, right? Dot is available, yeah. And if this is not true, which means that we don't have CUDA, then we want to use the CPU. And I also want to print this device just to check if this is actually true or not. So let's do that, and we might get errors because I didn't do anything wrong. This warning is fine, and we get some errors, that's fine. So let's do this instead, and open another terminal to be able to check this. So I'm gonna cd into Pytorch -tutorial, I think that's dash tutorial. Nope. Let's do this then. New cd into Pytorch.tutorial, and then I'm gonna type exit. I think it will be in the same. Nope, but it's fine. Cd Pytorch tutorial, like that, and we can clear this and ls here and cd into project files, project dash files. We're gonna cd this into this, and then we want to cd into transfer learning, like this, and then we want to run this main.py. So we're gonna type python 3 main.py like this, and this will probably give us the error, but it will be easier for us to read. So the problem here is that we don't find the entry name. It's in the no such file in directory hyperterra data/train. So it's probably because we don't have the train, or we typed the wrong name, and I will just copy this name and see if this works. Yeah, so I spelled the name wrong of the folder, and that's fine. So I'm gonna see if this works again. Okay, so now we get the yeah, so that's what I thought about. I think I actually let's do this instead and move this to like this one, and I'm gonna open the terminal here instead. So we're gonna cd into this, and then we're gonna cd into where is it? It's here, and then we're gonna cd into here. Nice. Now in the right directory, and we can go over to 1 here. Nice. Okay, so I spelled this wrong here. It's torch.utilities.data.dataloader, and it's clearly not the right path or the right yeah, it's basically typed wrong. So let's try to use torch.utils.data.dataloader. This is not found. Can I do this instead? So from torch.utils.data loader, oops, data loader, import I actually want to just do this, and then import data loader. Loader, like that. as DL maybe, and then we can basically just do DL here instead. And I will probably get the same error here, so oops. So if I try to run this program again, I will probably get the same error, I think. Yeah, it's okay. So now we have a smaller amount of errors. That's fine. So you cannot import data loader from torch.utils. So it's basically typed wrong in the documents here. For some reason, they typed it wrong. So let's see if I can find that data loader. So we are in the torch.utils, I think. Torch.utils.data. It's .data. Data. Okay, that's fine. Okay, let's see if that works. So let's go here and clear this and run this again. Yeah, okay, so and CUDA 0 works as well, which means that I actually use CUDA, so I can use my GPU. That's great. I had that problem for a year, and I actually finally fixed that. I will show you how I fixed that, actually. So if you want to use Pytorch and use CUDA, what you essentially have to do is go to the, I can just open a new tab here, go to Pytorch website. Don't install Pytorch by pip, by typing pip install Pytorch, and then you will be directed to this site. Don't use this. Don't use this because you want to use, if we go here and click on get started and go to, you want to have the stable version, and then we want to get your OS system. And then you want to use pip or conda, whatever you want to use, and you want to use Python, and then you can press CUDA here and use this command instead to install Pytorch. This will install the right CUDA version for Pytorch. So Pytorch is linked to CUDA if you have actually installed CUDA on your system. So that's great. So CUDA is actually working and the device is correct. So we can carry on with our project, and I think I should go back here. Nice. So don't go to this site and install Torch, because then you won't be able to use CUDA. That's a great advice for you guys. So this works. We can use CUDA now. That's great. So now we want to visualize a few images. So let's visualize a few training images so as to understand the data augmentations. So they create a definition, a function or definition, which is called image show, and this takes in a value of INP. This could be any type of value, and the title is going to be equal to none. So we don't have any titles, which means that we can get any image with any title we want. And now they display, so they basically just typed a string here just for clarification, and this function will display the images. So INP is going to be equal to INP.numpy. And the reason why this is not working is because the INP that we're gonna insert to the function is obviously a Pytorch or a NumPy value, and the mean is gonna be equal to the np.array. So we're gonna create an NumPy array here, which is gonna take in the same values as the transform do, I think, yeah, or the first value here, just to show you guys how the images is gonna look with these values. And then we also want to create the std, which is the standard deviation, and this is gonna be an array as well, or NumPy array with the other values. So these values represent the mean of the dataset, and this represents the standard deviation of those values of the matrix. And this is basically values that you use to train AIs or create linear regressions or non-linear regressions for your computer to understand what the data actually looks like. And if you are interested in that, then you have to know the math behind it, and I won't explain it here. And the reason why I know it is because I have a class in university that explains that. And now we're gonna basically take the standard deviation and multiply it with the INP, and then add it with the mean. So we create a function here, and then we're gonna clip this, so it's gonna be equal to numpy.clip the INP and 0 and 1, I think. Yeah, and then we're gonna show the plot. So plot.image show like that. This is gonna be a dot, not a comma, which is gonna take in the INP value that we get. And if title, so we're gonna create an if statement here for the title, is not none. So if we don't have a title that is none, we want to display the title. Otherwise, we won't probably. Why is caps lock in? So plt.title. So we're gonna set the plot title to the actual title, and then we're gonna pause. So plt.pause. This will basically just add some values like that, and the pause is a bit so that the plots are updated, basically. Okay, so now we want to get the batch. So I can actually add a new comment here. So pause a bit so that plots are updated. Like that, and pause is spelled wrong, by the way. Pause like that, and then here we want to get batch of training data. So the inputs and classes. So these two values will be equal to the next, which is the next value, and we're gonna iterate over the data loaders with the train data. I think this is going to be like this, yeah, like that. And then we're gonna make the grid as well. So make a grid from the batch we get, and out is gonna be equal to torch vision dot utils dot make grid, and this is gonna be the inputs that we get, and then we're gonna basically call this function here that we just created. So image show is gonna take out, and also the title, which is gonna be which we get from the inputs and classes. So title is gonna be equal to classes underscore names, which is gonna be x, and I think we're gonna loop over this. Yeah, for x in classes, like that. And I think I spelled it wrong. Yeah, like that. And class, not classes, class. And if we run this code, so let's go to our terminal and run this Pytorch again, or this function. So we get the problem that the directory object is not callable. So let's see if I did anything wrong here. Yeah, okay, so the problem is that we don't want to use these parentheses here. Okay, so I think that actually kind of worked. It's just that the okay, so this is basically what's going to happen, but for some reason the window didn't appear, and maybe it's because. Okay, so what if I change the layout on this to this and run this again? If this works. Okay, so the images is actually coming up. It's just that my tiling window manager doesn't recognize the window, but that's fine. This works. So training the module. Now let's write a general function to train the module. Here we will illustrate scheduling the learning rate and saving the best module. And I wonder if I want to. Let's create this same function in the same file. Okay, let's try that too. Oh. Okay, so let's do this whole definition of train module function. We can remove this image show here. I don't think I need all of these here, so I'm gonna comment these out. I don't think I need those. So we're gonna create a function that's called train module or model. We're gonna take in a model. We also want to in criterion. We want to take in the optimizer. We want to take in the scheduler. Oops. And the number of epochs, which is going to be a fixed value in this sense at the moment, but you can change this if you want to. And now we want to create a value since, which is going to be equal to time dot time. So we get time, and here we want to create. I'm just gonna check something here. Yeah, that's fine. Okay, so here we want to create a temporary directory to save everything. I think temporary. Oops. Temporary dir to save training checkpoints. So with temp directory, so we're gonna create a temporary directory as temp dir, and inside of this we want to create a value that is called best module parameters params underscore path is equal to the operating system. So we get the path of the operating system, and then we're gonna join that with the temporary directory that we create and the name, and we're gonna join that. So it's gonna be best module params .pt, I think. Yeah. And then we're gonna torch.save. So we're gonna save the module directory. Best module params. I think it's not the right. It's module.static path, right? Directory state path. So it's a state directory. Dict. And that it's fine, I think. The best module underscore params path. So we're gonna add that, and the best accuracy is going at the moment gonna be equal to 0.0, and this is gonna be a float because we're gonna use floats here. And we also want to yeah, so we're gonna create a for loop that is gonna run on the number of epochs, which is gonna be 25, and then yeah, so this is basically just gonna train the module. This for loop here is basically essential for our training. So for each epoch in the number of epochs, so in range, you could also, I think you can use the length here as well, but that's fine. In number of epochs, we want to print certain justifications so we can understand what is happening. This is going to take in the epoch that we iterate over. And this is going to be slash the number of epochs -1. So it's going to be like epoch 1 of 25, or since it's 0 indexed, it's going to be 24. But that's fine. So this will basically count the number of epochs that we use to train. The maximum is obviously gonna be 25, and then we're gonna just create a big line here, so we can type a minus token, and then just say duplicate this minus token 10 times. So we're gonna print this minus token in the row in the same row 10 times. This is actually quite interesting that you can multiply a string with a number to print it multiple times. That's interesting. Either way, so we're gonna each epoch has a training, which is training and validation phase. So for each phase, basically, phase in the train and also val, we want to so if the phase is equal to train, phase is equal to train, we want to do certain things, and if it's equal to val, we want to do some other things. So this is going to be model.train, and the model is something that we're going to import in the function, else we want to evaluate the module. So module.eval, like that, and outside of this if loop here, and we can also just create these here. So we're gonna set module to training mode. So this will set this whole thing here. We'll set the module to training mode, and this will set the module to evaluation mode. Set module to evaluate mode. Nice. And inside of this for loop, we want to type running loss, which is going to be a value, which we're going to store the values of the running loss, which is also going to be initialized to 0 in a float value. And we also want to have running corrects, which is basically the number of times it has correct values, basically. So this will save the value of the losses, and this will be the correct answers. And this is going to be a int, because we're going to just increase it. So we're going to iterate here, iterate over data. And Jesus, iterate over data. So for the inputs that we have, and I can't type here, inputs and labels in the data loaders we just created, which is phase, basically. We want to set the inputs to inputs to the device, which is using CUDA device, like that. And this 2 is not gonna be 2t here. So you're gonna set the inputs to the device, and we're also gonna set the labels to the device. And the device is basically saying that use CUDA to my device, which is the computer I use at the moment. And then 0 the parameters gradients. And this is gonna be optimizer dot 0 grad, which is gonna make us able to do back propagation later. We'll use that later. And now we're gonna get forward function here, which is basically the function that is going to be used to train and so forth. And this is basically also back propagation that we're doing right now. So we're gonna track the back propagation history. Only if we are in train mode, because in evaluation mode it's not worth to do. So with the torch dot set underscore grad, which is basically enabled, right? Yeah. Phase is equal to train, right? Yeah. Train. And the outputs is gonna be equal to module inputs. And then we're gonna do a wildcard here, so it doesn't really matter what we get. And preds is gonna be predictions. It's gonna be torch dot max, so the max outputs of a dimension of 1, I think. Yeah. And the loss is gonna be equal to criterion outputs and labels, like that. And here we use backward. Backward. Thank you. Plus the optimization. Optimize only if the phase is in training phase. Only if in training phase, basically. Yeah. So I think so. If the phase is equal to train, which is gonna be a string, by the way, train, like that. Loss.backward, which is the backward propagation. So I'm gonna backward propagation the loss backward, and we also want to step the optimizer step, like that. And this, now after this we will get the, I think this is outside of the width. So statistics running loss, though running loss is equal to plus loss.item, so we get a certain item and multiply that with the inputs size, which is gonna be 0. And then we have running corrects, like this, is gonna be plus equal to torch dot sum, so we're gonna get the sum of the predictions, which is gonna be also equal to the labels dot data. And if the phase is equal to phase equal to train, we want to step the scheduler as well. So it's basically a function that, not dot train, it's gonna be dot step. So the function here is essentially, if we are in train mode, we do this. If we are in valuation mode, we do the other things. And the epoch underscore loss is equal to running loss, running loss divided by dataset size, which is gonna take in the phase as well. So this will depend on the valuation phase and also the training phase. And then the epoch accuracy is gonna be equal to accuracy is gonna be equal to running, so the correct running, and use the double function here, divided by the data sets size, which is going to take in the phase as well. And here we're going to print the phase we are in and also the loss. And why is this? Nice. And epochs underscore loss, and this should be, yeah, that's fine. For F epochs, it's not epoch loss. Nice. Underscore for F, and why is this here? And the accuracy is gonna be displayed like this, and this is gonna be outside of the brackets. Accuracy is basically the epoch's accuracy of for F. Nice, and now we're gonna deep copy the module as well. So deep copy the module. So if phase is equal to value or evaluation, and the epoch accuracy is better than the best accuracy, and by this I have to change that. Best underscore accuracy, I'm gonna change that. Boom, there we go. Now we have, yeah, so if the epoch accuracy is better than the best accuracy that we have, we're gonna set the best accuracy to the epoch accuracy. This is basically a way for you to evaluate the module that you want to train. And then torch.save, so we're gonna save it. The module.state directory. This is something that you have to do for every single module that you use. And also the module params path. And after that, I think this is outside of the for loop epoch, right? Yeah. So outside of this for phase, I think. Is it for phase or is it for epoch? This is for phase. It's out of the epoch. we basically, so this will be, if we collapse these, so here, and this is gonna be, I think it is just inside the width. Yeah, it's gonna be print, just normal print. This will print nothing, and inside of the function, we want to get the time elapsed, so we're gonna have the delta time elapsed into time, which is the current time, minus the start time, which is gonna be since. And then outside here we want to just print some more values. Training complete in the time we just calculated, so it's gonna be time elapsed. Divided by 60, so we will normalize it by 60. And this is gonna be for f, right? No, it's gonna be 0f, 0f, and then m here, and this will be calculated within the percentage, so time elapsed percent 60, like that, and this is gonna be 0f seconds. So this is gonna be, this will calculate the time elapsed in minutes, and this will calculate the time elapsed in seconds, basically. You don't have to do both, but it's fine. And then we want to just create or print the best value. So best value accuracy, can do ac is equal to best accuracy, basically. And this is gonna be 4f. Like that. And also here we want to load the best module, module weights, and then this will be module.load underscore state directory or dict, and this is gonna be torch.load best module path, reference path, and then here we want, after this, we want to return the module. And I think this will be actually inside the width temporary, I think. Where am I tweaking? The module is actually, I think the module is, yeah, okay, so this whole thing here will be inside of this function here. So print is going to be, so this print value here will be inside here. So we're gonna do that, and also do the same thing with this. And here we want to do return module. So we're gonna return the module. So this function basically trains the module and then also calculates the best accuracy based on the weights. So I think that's fine. We can collapse this whole function here. Boom. And now we want to visualize the module predictions, basically, and use the function. So we can just create a visualizing or the visualizing module function, basically. We create another function which is gonna be visualize. This is something I have to look into more in depth, because this is an essential way to train generalized modules. It could be a LLM, it could be a RNN, CNN. Was training is equal to module dot training, and then I'm gonna evaluate the module dot eval, and then images so far, which is gonna be initialized to 0, and then the figure is gonna be plt dot figure figure like that. And inside of here we want to do with torch dot no grad that for I. So we're gonna do a for loop and loop over the inputs and labels like that. In enumerate the data loaders, which is going to be the the val or the valuation. We want to set the inputs equal to the inputs to module, so inputs dot to device, right? Yeah, device, and then we also want to do the labels as well. Just labels dot to device, I think. Yeah, and then we want to set the output value outputs equal to module that's gonna take in the inputs like that, and the predictions and the wildcard. It's gonna be equal to torch dot max outputs. Oops, outputs 1, and the outputs is not defined for some reason because I typed that wrong. So this is gonna be equal to that. And then for j, so it's another loop in range of the inputs dot size, and we are just gonna use the first row basically, the matrix. Images so far is gonna be +1 plus equal 1, and the AX is gonna be plt dot subplot. So this is basically just creating the subplots divided by 2, and the image so far as well. That, and the axis. So this function basically just creates our own plots, and it's not related to the module itself. Title, it's gonna be if predicted class names, which is gonna take in the preds. This is gonna be a list as well. That, and it's gonna be j because we're gonna loop over all the predictions. And then we're gonna call the image show function that we created. This probably won't work because of my tiling window manager, but if we don't get errors in code, the code works. CPU and also dot data takes in the j, so we're gonna loop over that. And if the image has so far is equal to number of images, we want to do module dot train, and the mode is gonna be equal to was training, and then we're gonna return, and this will return. And here we want to essentially just do module dot train mode is equal to was training. And this is basically just gonna fine tune our conventional net. So let's do that. And I'm not gonna type this. I don't think this is actually important. So we're gonna get a value which is the fine-tuned module ResNet, and this weights is gonna be this value here. This, I think this is standard seed for weights. Number of fine-tuned iterations basically here. Here the size of each output sample is set to 2, and alternatively it can be generalized to n.linear, the number of to the device, and then criterion is no cross entropy loss, and the optimizer is this one, which is for the fine-tuned, and this is also decay. So observe that all parameters are being optimized, and then decay all by a factor of 0.1 every 7 epochs. So let's see if this works. And we probably will get errors because there's a lot of code we wrote. So let's test this out. It's basically a script on almost 200 rows. So this will probably give us errors, but we'll fix that. And it didn't give us errors, I think. Okay. So it didn't print, but we didn't get errors, so we typed everything right. I'm just wondering where it will... this is basically the downloading, so I think we did everything correct actually. Downloading here, and if we check the No, that's fine. So we downloaded the module, that's fine. It should take around 15 to 25 minutes on the CPU. On GPU though, it takes less than a minute. Wow. So let's test this out. Okay, boom. Okay, so 0D or 1D target tensor expected multiple target not supported. And I don't know what this is actually the problem, but let's see. So the problem is in the line of 188, and then it goes to line 107. So it's 107 we should go and look at, which is inside of the train module. So 107, it's this one here. So I think I just typed something very small wrong here. So I'll just copy the whole code here. It will be essentially the same code. So I'm gonna do that instead. Let's see if that works. Data set sizes is not defined, so I typed that wrong as well. And this will be in the line 117, so it's a better one. It's something I typed wrong, obviously, because you type some stuff wrong. So data sizes is not defined, and where is this defined? This should be defined in, I think, up here. Yeah, so it's this value here. So let's just set the name to this instead, like that, and now it should be defined. So let's try this out. Yay, it kind of works. Wow, okay, nice. Let's see how long this takes. They said about a minute, so I hope this will be fine, and I think it's fine. So the code works, and we are basically training our image classification module right now. And the accuracy is basically 90%. And it will probably be around that. I don't think it will go higher than like 93 or something. As you guys can see, it's around 90%. But that's still good. 90% is great. And I think if you have a larger dataset, the accuracy will increase as well. So yeah, let's try to use the CPU just because it's fun, you know? Let's see how long it takes. So the epochs is fine, and this should be done. So yeah, that is fine. You're using torch.load, that is totally fine. This works, no problem. Let's visualize and then use the CPU just to test it out. So we're just gonna add this bit of code, which is calling the visualizing function that we just used, and we're gonna have to train the module again. And this probably won't appear because of my tiling window manager. But let's check that out. And I'm also gonna see if the CPU actually works on this. It would be quite fun. So it's around 90%, that's fine. It's actually decent. And it's still doing quite good. And by the way, if we go up a bit, and if we check these are actually 10 minus tokens, because we multiply with 10 in the print, so that's good. %, around that, yeah. Okay, so it's visualizing and then it's closing it. But you can see it works. So let's test out the CPU, and I think interference on custom images, further learning. So this is basically, we have basically done the main thing. But let's try out the CPU, and then I will try to explain all the things a bit more. So we have to check on the torch. Yeah, it's this one basically. So if we remove this and type this instead, we will change to the CPU. So device is equal to, device is equal to torch dot device, I think, yeah. And then we will take in CPU as a string here. If we do that and train the module again, we will see this will probably take forever. It's basically taking forever to use the CPU. Holy shit. Yeah, it's definitely a power upgrade to use the CUDA version. Yeah, this is not going so great with the CPU. Oh my god, this is actually bad. This is so bad. What is 24 divided by like 20? So every epoch will take about 2 minutes or something. Oh, that's terrible. Okay, yeah, let's stop this. This is taking too long. We will not even get 1 epoch. Holy shit. Yeah, that's fine. Clear, and we're gonna set this to the CUDA version instead. So let's go and change that. Remove this and go back with the device, and let's just run it again because it's fun. Yeah, that is definitely better. So much better. Okay, nice. Okay, that's working. Okay, let's try to explain this in a bit bigger detail, and I don't think I will go over this whole thing. So fixed feature extractor, and I don't think we need to do this. So in inference on the custom dataset, use the train module to make predictions on custom images and visualize the prediction class labels along with the images. So you can use custom images as well if you want to. So here's a custom image, predicted bees. You know what? I won't type this because this is basically not for the whole module, but you know, let's do this. Let's see if we can. So instead of this, we want to add another function which is visualize predictions, and data transforms is this whole thing is probably not defined. But let's just fix that. Oops. Like that, and we're gonna remove the data as well. So it's just gonna be that module.convention. It's fine, I think, and I think let's see, module.convention. I think we have to. Is that not defined? I think that's defined. Maybe it's not. No, it's not. Oh, what? Okay, so we have to add this as well. So let's do that. So here we want to add this, and then we want to add this as well. Add it here. This is basically the same code that we used, just to a specific image instead. And we did that and did that. So let's see if this works. You can, by the way, see my CPU here. It's about 50%. Now it's 0. Now it's 60. Now it's 61. And we can see the memory being used here as well. So it's using 7,000 megabyte, I think. So it's about 7 gigabytes of memory used. That's quite funny. So obviously the evaluation is taking a lot, it's going a lot faster because of the CUDA library. That's great. I like this. Kom inte in. Kom inte in. Stäng. Mormor, stäng. So now we're gonna train for the just one image, and it's probably gonna go a lot faster. Yeah. The accuracy is also quite a lot higher. Boom, and now it's gonna show me the image here. Oh, okay, so data, it's this, nope, whoops. It's this value here that is not defined. Either way, it doesn't matter. It's fine. So this works, and we are basically done with that. So, I think I'm going to end the stream here and make another stream to explain this whole thing. But this is fun. We have now created an image classification module that we train and also check multiple times if the accuracy can be better. And we're also using CUDA on our own local system. So that's really cool. Yeah, but that's all for today, guys. I hope you have a great day, and thank you for watching.